Hello everyone, myself Usha Mireshkar, Selection Grade Lecturer, Electronics and Communication Department, Government Polytechnic, Belgaum. Today in this particular session, we are going to learn about the subject Advanced Communication, that is for the 5th semester Diploma Electronics and Communication Engineering students here. In this particular subject, the unit cover is the second unit, that is Radar Principles and Applications. In this particular unit, it is the 8th session. Now the contents which we are going to cover in this particular topics are, first one is the Doppler effect, concept of continuous wave radar, block diagram of continuous wave radar, advantages, disadvantages, and applications. Now the Doppler effect. What do you mean by the Doppler effect here? What is this principle? According to the Doppler effect, the apparent frequency of electromagnetic wave depends on the relative radial motion of the source and the observer here. That is, the apparent frequency depends on the relative radial motion of the source and the observer. For example, if the source and the observer are moving away from each other, if the source and the observer are moving away from each other, the apparent frequency will decreases here. And in the same way, if the source and the observer are moving towards each other, then the apparent frequency will increase here. Now in case of the radar here, we can analyze, just observe this animation here. This is the radar station and this is the target here. For example, the radar station is radiating the frequency ft, or it is transmitting the frequency ft here, and it is receiving the frequency fr. It is transmitting ft and it is receiving fr. Now if both this source and the target both are stationary, if both are stationary, then the received echo signal, the radiated signal will strikes the target and it will be coming back, reflected back towards the radar here. Now the received echo signal, if both are stationary, will get the same frequency here. Whatever the transmitted will get same as that received echo signal's frequency here. But now consider the first case, if the source and the target both are moving away from each other. That is, suppose the aircraft is moving away from the radar station now. If they are moving away from each other, then the radar station will radiate the ft here. It is striking and fr is coming back. But now in this condition, the received signal is not same as the ft, but it will changes here. Since the target is moving away from the station, the received frequency will decreases. Therefore, fr is equal to ft minus fd. That shift will be there. FD is called as the Doppler shift. In the next condition, suppose the aircraft is moving towards the radar station. If it is moving towards the radar station, in that condition, what will happen? Since the target is moving towards the source here, therefore, now the whatever the signal it is radiated, it is ft here. Now the fr is coming back. Now the target is moving here towards, means it is close to the station. Therefore, whatever the received frequency will be there, that will be increases here. Therefore, the received signal will be more than ft plus fd. That fd is called as the Doppler shift in the frequency. Therefore, if the source and the target both are stationary, we will receive the same frequency. But if both are in motion or any one of them in motion, then what will happen? The shift in the frequency will occur. Therefore, fr is equal to plus or minus, that is ft plus or minus fd. That fd is called as the Doppler shift frequency here. Through this picture, we can analyze that statement here. Now consider observer 1 and observer 2 here. Observer 1 and observer 2, and this is the source here. For example, ambulance, it is generating the siren here. Now since ambulance is moving towards the observer too, therefore the frequency received here is more than that of the original. Therefore it is ft plus fd. And here if you observe the observer 1 here, the source is moving away from the observer 1 here. Therefore here it is ft minus fd. Therefore it is reducing. Relative frequency will reducing here. In the same way here, suppose this is the original frequency during the stationary condition here. When it is not moving, this is the frequency. Now suppose this ambulance or this source is moving towards the observer, then the frequency is increasing. We can make out here. This is the original and this is the increased frequency. Now suppose the ambulance is moving away from the observer, then it is frequency reducing from the original. This is the original and this is the reduced. Therefore it is either ft plus fd or ft minus fd here. Same here, that is, this is the radar station here. This is the radar station. It is radiating the signal, for example, f0 towards the target. It is radiating the signal f0 towards the target here. Now first condition, let us assume target is moving towards the radar station. This is the target. It is moving towards the radar station. Then what will happen? This is the transmitted signal here towards the target. Now the target is moving means the echo signal which is coming back, it is having frequency more than the original here. You can observe from the graph here. Therefore it is f0 plus fd because radiated signal is f0 here. Therefore it is f0 plus fd. Similarly, in this condition, the target is moving away from the radar station here. The direction of the movement is, it is away from the radar station. Therefore, the echo signal received is f0 minus fd. From the graph also we can observe that the waveform is having the frequency less than the original frequency here. Now how to calculate that fd, shift in the frequency? How to find out that fd here? Fd is given by 2 Vr divided by lambda. Fd is given by 2 Vr divided by lambda, where Fd is the Doppler frequency shift and Vr is the relative radial velocity of the target and lambda is the wavelength of the signal here. Therefore, if we know this shift in the frequency and this particular wavelength, we can easily find out the relative radial velocity of the target here. Therefore, this Doppler effect is used to find out the radial velocity as well as the in the continuous wave radar, that is the distance also we can find out in the FM continuous wave radar, and also we can find out the whether the target is moving or not. But in case of the plotting purpose, this Doppler shift is not used. Only in case of the finding velocity, distance, and whether it is moving or stationary here. The Doppler effect, that is Ft is the transmitted frequency, Fr is the received frequency, Fd is the Doppler frequency shift. Then what is the equation here? Fr is equal to Ft plus or minus Fd. Therefore, shift in the frequency is occurring here. Through this waveform, again we can analyze here. Suppose this is the target here. As indicated, this is the target. Now in the first waveform, the target is moving away from the station here. Here it is the station and the target is moving away here, as the arrow mark indicates. Therefore, this is the transmitted wave and this is the received echo signals wave here. The received echo signals wave's frequency is less than the transmitted wave. We can find out from this graph here. In the same way, in the second condition, suppose the target is moving towards the station here, then this is the transmitted signal and this is the received echo signal. Now the received echo signal's frequency is more than that of the transmitted signal here. Therefore, here it is motion is towards the station, means the frequency is increasing here. Next, through this small video, we can get clarification about that Doppler effect here.
In this illustration, we see a radar tower with two adjacent mountains. When the radar tower emits a pulse, the mountains cause part of the pulse to reflect back to the tower. When the tower picks up these reflections, they register on the screen on the right. Now we see how a radar tower tracks a moving object. We see how every time the radar pulse hits the jet, a portion is reflected back. The radar display on the right shows the path of the jet. If we fast forward the animation, we can see how a jet being tracked in real time would appear. This is what a radar screen looks like with lots of reflections. See how difficult it is to track the moving object through all that clutter? To solve this problem, we use the Doppler effect, which is the change in frequency of the radar wave when it encounters a moving object. When the pulse hits the stationary tank, it reflects back at the same frequency. However, when the pulse hits the jet as it is moving away, it reflects back with a lower frequency. Finally, as the jet returns, the pulse is reflected back with a higher frequency because the jet is moving towards the tower. All we need to do is add a filter to the radar receiver that eliminates returning pulses with an unchanged frequency. When a pulse returns with a changed frequency, it is allowed through the filter and onto the display. So now when we are tracking the jet on the radar, we only get the moving object with none of the clutter.
Okay. Now let us have one more video.
Applications of Doppler effect. The illustration shown here will help you understand the Doppler effect. I'm sure you would have heard an ambulance speeding past you. That is, the pitch of the siren increases as the ambulance approaches you, and the pitch decreases when the ambulance moves away from you. There is a similar apparent change in the pitch of the sound heard when the source of sound is at rest and the listener moves towards or away from the source. The change in pitch is due to a shift in the frequency of the sound waves. Based on these observations, an Australian physicist and mathematician J.C. Doppler proposed the Doppler effect in 1842. According to the Doppler effect, the apparent change in wavelength of sound or light is due to the motion of the source, observer, or both. Doppler effect is observed in light also. Suppose a star recedes from Earth, then the frequency of the light emitted by the star decreases or wavelength increases. Thus, the spectral lines are shifted towards the red end of the spectrum. This is called redshift. Similarly, when a star moves towards the Earth, the spectral lines shift towards the blue end of the spectrum. Applications of Doppler effect. To find the velocity of a speeding car. Let us see how a traffic police catches speeding motorists. Short waves emitted from an observation center are directed towards the speeding vehicle. These waves are reflected by the car to the observation center. By calculating the shift in the wavelength, the velocity of the speeding car can be determined. To determine the depth of oceans, we can apply the Doppler's effect for estimating the depth of the oceans. For this, we make use of a sonar. A transmitter from a ship transmits sound waves towards the ocean floor. These waves are then reflected by the ocean floor and are received by the receiver. Note the time taken by the waves to come back to the source. Now we can estimate the depth of the ocean by using the formula T is equal to V into T by 2, where V is the velocity of sound waves and T is the time taken. To calculate the speed of astronomical bodies, the Doppler effect of light can be used to measure the speed of stars and galaxies. The spectrum of light coming from the planets and stars are photographed over a long period. By observing the Doppler shift, one can conclude whether they are moving towards or away from the Earth. To study Saturn's rings, concentric rings surround the planet Saturn. These rings reflect light and are not self-luminous. The Doppler shift of light reveals that the rings are not continuous, but they consist of many particles.
Okay, now let us study the block diagram of the continuous wave Doppler radar. This is the block diagram here. If you observe the blocks, first block is the continuous wave transmitter oscillator, which is generating the continuous wave signals here. That is of frequency ft. Now this is the antenna section. This is the receiver section here. First stage is the detector stage. Second is the audio amplifier, and this is the frequency counter here. Now if you observe the circulator here, the main purpose of the circulator is same as the duplexer in case of the pulsed radar here. That is to protect the receiver section from the strong signals of the transmitter section here. While during the transmission process, this will be saved here or protected here. And during the receiving process, the signals are directed towards the receiver here. That is means it is playing the same role as the duplexer in case of the pulsed radar here. Now the continuous wave transmitter, it is transmitting the ft through this antenna. Those are radiated and the echo signals are coming back here. And depending on the position of the echo signal here, for example, if you observe this animation here, if the target is stationary, means you will get the frequency same here. Whatever the ft is transmitted, you will get the echo signal's frequency as the same ft. But if it is moving either away from the station or the towards the station, there will be the shift in the frequency. Therefore, the received echo signal will be having the frequency ft plus or minus fd. ft plus or minus fd. That is also given to the detector point, and some part of the transmitted signal ft is also fed to the detector part here. Now these two signals are combined to remove the ft, and output of this particular block is the fd, that is the Doppler shift. And if you know the Doppler shift, that can be easily calibrated at the relative velocity. Therefore, that is first it is amplified here and given to the frequency counter, and that is displayed in the form of the relative velocity of the target here. This is the simplified block diagram of the continuous wave Doppler radar. The main sections in that continuous wave Doppler radar are continuous wave transmitter oscillator to generate the continuous oscillations here, circulator for the protection of the receiver circuit, and since it is using the same antenna section here. Next is the detector here. It is receiving the signal from the echo signal as well as part of the transmitted signal, such that it will give output as the FD here, and that FD Doppler shift is amplified and it is given to the frequency counter, and it is calibrated as the particular measure of the relative velocity here. Again, one more version of the continuous wave Doppler radar here. Here if you observe, this is the continuous wave transmitter here, transmitting antenna. It is generating the continuous waves and it is given to the transmitting antenna to radiate the signal here. Now the part of this signal is taken in the mixer where the local oscillator signal, that is IF signal, is added here. Therefore here the output will be this FT plus IF here. Both are added. Next it is given to the filter section to remove the unwanted. That is mixed with the mixer 2 here. In the mixer 2 we are having the received echo signals, that is FT plus or minus FD. Now in this section that FT is removed and that is given to the particular IF amplifier here to amplify the signal. And in the detector section, that particular IF is removed and you will get the output as the FD here. That is the Doppler shift, and that is amplified and measured as the relative velocity. Now let us analyze this block once again. Now see here, this is the continuous wave radar. We are having the transmitter section and the receiver section here. Now if you observe here in the continuous wave radar, that it's a continuous wave transmitter here. This will transmit the signals here. Now through this transmitting antenna, this transmitter or the oscillator which is generating the continuous waves, those are given to the transmitting antenna and those are radiated here. Now the part of the transmitted signal, it is given to the transmitter mixer, where one more signal is added, that is the IF oscillator signal. In this particular mixer, the part of the transmitted signal and the IF oscillator signals are mixed, and this mixer is connected to the receiver mixer. You can observe this line here. It is connected to the receiver mixer here. Means the receiver mixer is getting the signal, that is FT plus IF. That is the part of the transmitted signal and the IF signal here. Now at the receiver section, what will happen? That is, receiving antenna will receive the signal, echo signal, that is either FT plus or minus FD here. Plus, it may be plus or it may be minus here. That is given to the mixer, and one more signal which is coming is that is FT plus IF. Now that in this mixer FT is removed, and here you will be having the output as that FD plus IF only. Now that is amplified in the IF amplifier here. Now that is given to the detector section to remove the IF, and the output of the detector is you'll get the only FD, and that FD is amplified here. That FD is amplified because we are having the information in the FD. That FD we are converting in the form of the relative velocity here. Now that is amplified and that is given to the indicator. Indicator will indicates the FD in the form of the relative velocity here. Therefore, this is the simplified working of the continuous wave radar. It is giving the information about the relative velocity of the target. Now advantages. What are the advantages of this continuous wave radar here? First one is it is the Doppler radar circuit. It is simple here. Continuous wave radar Doppler circuit is simple. Second is the power consumption is low here. In the circuit, the power consumption is low. And the equipment size is small. Unaffected by the presence of the stationary targets here. If in between some stationary targets are also there, that is unaffected here. Can measure the large range of target speeds very quickly here. It will give the speeds of the relative velocity here. Next are the disadvantages here. Its transmitting power is limited, which reduces the maximum range here. That is, it is having a limited transmitting power, such because as we know, the range depends on the transmitted power here. If the power increases, means range will increases, but it is having the limited option, means the range will be reduced range here. And easily it is confused by the presence of the large number of the targets here. And one of the major disadvantage or the drawback of the continuous wave Doppler radar is it is incapable of indicating the range of the target. Only it can identify its relative velocity, it can give that measure, but it is incapable of giving the range of the target. This is one of the major disadvantage of this CW radar here. Applications. It is used in the aircraft navigation for speed measurement. It is also used in the radar speedometers used by the traffic police to find the speed of the vehicles, whether they are moving in the safe speed or not here. Okay, students. Now let us have some MCQ quiz here. Try to answer honestly and grade yourself for out of 10 here. That is the first question is the Doppler effect is used in, pick the incorrect answer here. The options given are moving target plotting on the PPI, moving target indicator, continuous wave radar, FMCW, that is frequency modulated continuous wave radar. Yes, try to answer this question. Yes, any guess? Yes, right. The correct answer is answer A. That is moving target plotting on the PPI, because we are not using in this particular application here. The second question is the Doppler frequency is large if the given options are transmitted frequency is small, relative velocity of the target with respect to radar is large, relative velocity of the target with respect to radar is small, size of the antenna is large. Let's try to answer this one. Yes, the correct answer is B. That is relative velocity of target with respect to radar is large here. Third question. A frequency shift of sound, radio or light waves that occur as the result of the relative motion between objects is called the deflection, reflection, Doppler effect, none of the above. Yes, any guess? It is depends on the relative motion. Therefore, the answer is C, that is Doppler effect. Next is the, pick up the incorrect sentence here. Continuous wave radar works on the principle of Doppler effect. Continuous wave radar gives accurate measurement of the relative velocity. Continuous wave radar indicates the range of the target. Continuous wave radar is unaffected by the presence of the stationary targets. Yes, which option is correct? Try to answer. Yes, correct answer is the option C, because continuous radar indicates the range of the target. It is the false sentence here, incorrect sentence here, because it is not capable to give the range here. Fifth one, if the source and observer are moving away from each other, the apparent frequency will increase, decrease, remain same, both A and B. It may increase or decrease. Which is the correct answer? If they are moving away from each other, source and the observer are moving away from each other. Yes, any guess, students? Yes, right. It is the B is the correct answer, because they are moving away from each other. Next question, that is, in Doppler effect, the receiving frequency is given by the equation Fr is equal to Ft plus or minus Fd. Fr is equal to Ft divided by Fd. Fr is equal to 2 Fd Ft, and none of the above options here. What is the correct equation for the Doppler frequency that shift here? Yes, it is the A, that is Fr is equal to Ft plus or minus Fd, received frequency, because we will be having the shift there. Either it may be plus or it may be minus. The Doppler frequency Fd is given by the equation Fd is equal to 2Vr. Fd is equal to 2Vr divided by lambda. Fd is equal to lambda divided by 2Vr. None of the above. Which is the correct answer? That is equation for the Fd. Yes, any guess, students? Yes, it is the answer B. That is Fd is equal to 2Vr divided by lambda. Okay, in the next session, we'll try one more MCQ there. Thank you for watching.